Hello, everyone. My name is Alex Baker, and I'd like to welcome all of our new and existing users to the Moldex3D 2025 standard training. Just a couple admin things before we get started here. Please keep your microphones muted throughout this session to keep the distractions to a minimum. This session is being recorded, and the recording will be uploaded to our YouTube channel, Moldex3D North America. All attendees of this training will receive a link to watch that channel at your convenience or to share with your colleagues. Any questions throughout the session can be sent through the chat section of Teams, and we'll have to answer those questions live and in the Q&A session at the end of this training. This session is meant to be interactive, and to follow along, you'll need two things. The first one is the Moldex3D Studio application. This is what we'll be using to set up, run, and interpret the results of our analysis, so you'll want access to that on the desktop, and the installation should have placed it there for you automatically. If you have a previous version of Moldex3D installed, you'll still be able to follow along, but there might be some new features you don't have access to quite yet. Please also have the consumer folder downloaded and extracted. It contains the model and pre-run simulation file we'll be using throughout the session. If you have not installed Moldex3D, then feel free to follow along visually, and you can review the recording at your convenience. The agenda today is as follows. The first hour, we're going to go through setting up a simulation model in Moldex3D. So importing the geometry, setting up your runner system, cooling system, all of that. The second hour is going to go through meshing theory and setting up the final aspects of your simulation. That would be your material, process, and any sort of computation parameters. And then finally, in the last hour, we'll go through the post-processing, the result interpretation, what happens after the simulation has been run, how can we get a meaningful readout of our analysis. All right, so we'll go ahead and get started in the Moldex3D Studio 2025 application. You can go ahead and open that up straight away. And when you open up Moldex3D Studio, you're going to be faced with four options, but really just two. We have new and open. New allows you to create a new project file, and open allows you to open an existing project file. We'll be using both of these in this training, but for now, let's go ahead and click new. This is going to create a new iterative structure for you to run your analyses. The default name of this project is going to be MDX project followed by the date, and it will always be that when you create a new project. So I recommend you to always change this name to be something a little bit more meaningful. We'll call this standard training. The location, we always recommend to be on the local drive. The local drive is where the solvers are going to be stored, and so your simulation will be most efficient if there doesn't have to be a constant communication back and forth between your solver and your project file. If you put your simulation on a network drive or an external drive or some other location that is other than the local drive, there has to be an additional communication that's established. In the best case scenario, that can cause your simulations to slow down, and in the worst case scenario, that connection is broken and your simulation is forced to terminate. When you install Moldex3D, there's a folder already established automatically that is called the MDX working folder. So that might be loaded in automatically. I might recommend you guys for this training to establish your project folder on your desktop, just so you can access it a little bit easier. But anywhere on the local drive will be certainly fine. Once we've established the location, you can press OK. And that will create our project structure. Over on the left side, we see what's called the project tree. This is where all of your simulation runs are going to be stored. You can see Moldex3D has created run 1 for us automatically. So we'll see that this will populate as we incorporate and add more and more information into our simulation. Along the top side is what I call the ribbon. And the nice thing about Studio is that the procedure is really easy to follow. All you have to do is go from left to right across this top ribbon, and the interface will route you around automatically. That being said, we're going to start all the way at the left side of the ribbon where it says new run. We've actually already gotten our first run automatically, so we actually don't have to interact with this, but under the dropdown, there's a couple of options that I'd like to note. So new run will allow you to create a brand new run from scratch. Copy run is probably the most used function in Moldex3D. This allows you to duplicate an existing data set. You can make a single iterative change to that data set, rerun the analysis, and then Studio is really good at being able to compare different analyses to one another in an apples to apples manner. So you can really get the meaning out of that iteration or that variable. Import run allows you to bring runs from other projects into this one. And then we also have a couple of DOE options that are available as well. But those require an established run to be set up before we can activate that functionality. Like I said, Moldex3D has created the first run for us automatically, so we can move to the right of new run, which is our Moldex3D solution. If you click on the dropdown where it says injection molding, you'll see a bunch of options if you have the license modules available to you. If you only have the injection molding module, or maybe a couple of these modules, you won't see as comprehensive of a list as I have here. But we are going to be using injection molding for this training. Note that there are some other advanced methodologies that we have available in Moldex3D, and you can ask questions about those. I'll answer those at the end of this session. To the right of that is our meshing style. We have 3 different meshing styles in Moldex3D. Solid is what we'll be using 99.95% of the time. It's pretty much the standard meshing style for Moldex3D at the moment. And so this is what we call the boundary layer mesh type of meshing method. Below that is eDesign. This is the voxel type of meshing method. This will be used if we can't create a mesh in solid. And then shell is a different type of solver, whereas Moldex3D, given the name Moldex3D, we like to use 3D solvers and 3D mesh for all of our analyses. And solid and eDesign both give us a true 3D mesh. Shell is a 2.5D mesh that you could use to compare to other shell solvers. However, we prefer to use solid and eDesign. Mostly solid. To the right of that is the import function. All right, so I'm going to hit the import geometry button. If you click on the dropdown, you'll see import geometry there as well. I do recommend against using the auto heal just because sometimes the auto heal can take a really long time to import, and we want to go through and heal the cavity if it is necessary to fix ourselves. So we won't use the auto heal. We'll use the regular import geometry function. All right, and then I'm going to ask you guys to route to the consumer folder. I mentioned that you should download the consumer folder. We'll go into that consumer folder and we'll find the CAD data folder. This folder actually is blank by default. If you were to go into this project's folder structure, you'll see that the CAD data folder is a blank folder, and it's just a place for you to store input files like the step file that you use for your simulation, like some of the outputs that you get from the analysis, anything you want to, you can store in here. It's more of an organizational folder. We're going to find the step file called consumer.stp. We'll find that step file, and you can import that directly into Moldex3D. Now, in this case, we are using step file because it is the most universal CAD file type. However, we do have the option to import other types of files as well. You can see from this dropdown here, you can see all the different native CAD files. We have Parasolid files, we have IGS files, we have PRT files for NX, JT files. For Creo, we also have PRT files, and actually introduced in 2024, we have the ability to import the SLD PRT file type from SolidWorks. And so we have a lot of different file types that we have the capability to import, and it just depends on what the output you had from your CAD system looks like. Now, before I go too far here, I want to note some mouse controls. You might have just seen me rotate. You can rotate using the right click drag or middle mouse click drag. If you hold the shift button on your keyboard, you can pan your model. If you hold the control button on your keyboard and right click drag, that will allow you to zoom in a little bit more fine based on the center of your system. You can see a little target right here. If I left click on a model, that will select the model. That'll be useful for several functions in Moldex3D. And if you right click on a selected model, you'll see a short list of functions. We won't really use these too much in this training, but if you wanted to access some quick functions, you can highlight the model, right click, and you'll see those options. In Moldex3D 2025, we have introduced the ability to change your mouse configuration. So if you go up to your preferences, and this is in 2025 once again, you can go down to keyboard and mouse, view manipulation, and you can change your mouse mapping depending on what type of system you use. So you can see all of the different systems here, and you can also even create your own user-defined mouse controls. So you can make the experience in Moldex3D as fluid as possible as compared to your CAD system or other softwares that you might already be using. All right, now once we've imported our first geometry into Moldex3D, you'll actually see the ribbon has shifted automatically from the Home tab over to the Model tab. Whenever we go to a new tab, we're just going to go all the way to the left and work our way from left to right. All right, so the first button here on the very left of the model tree is import geometry. So if I had other objects that I wanted to import besides the part, let's say I had my runner, my cooling system, my inserts, my core and cavity blocks, my entire mold geometry, if you wanted to, you can import all of that information. In this case, though, we just have the part, and we'll be adding all of the other components of our simulation using the Moldex3D quick functions. So we'll see a bunch of those. Moving on to the right of the import geometry allows you to check the geometries that you imported. I'll hit check geometry. That's going to check for four things, actually three things. It'll check for free edges, tiny edges, and sharp face angles. Free edges will happen whenever two surfaces are disconnected from one another. Tiny edges, as the name suggests, are just very, very small feature lines. So if I turn these on, select, we can see that maybe they're just really, really small feature lines. And then sharp face angle is when two surfaces come together at an angle that is difficult to get solid mesh in that volume, which I have one example on here, but it's kind of difficult to route to. So we'll glance over that for the time being. Now, if I wanted to fix these, there's two options. I can either do so manually by either going back to the CAD system, or we have some short functions here in the fix geometry tool. However, almost all of the time, we will prefer to go out to CAD Doctor, which is a function that allows us to um, tune the step file that we've imported more towards the Moldex3D tolerances rather than your CAD tolerances that you exported from your CAD system. All right, so I'm going to go over to the CAD Doctor application by hitting the CAD Doctor button here. If you don't have CAD Doctor installed, you might not see this button available to you. If that's the case, that is okay. This geometry will still work without being fixed, but I'd like to go through the fixing procedure of Moldex3D CAD Doctor, just so we can get a feel for how quick and easy CAD Doctor is to use and how necessary it is in some cases. Now, the nice thing about CAD Doctor is once the model imports, we actually only have 4 buttons to click, generally speaking. All right, so we've imported our geometry. The first 3 buttons of the 4 are actually right next to one another over on the left side of the interface. And we're going to click them from left to right. The first one is check. This is going to run a 16-step checking procedure that will look for any potential issues or maybe even just translation problems between your CAD system and Moldex3D. If a surface is missing, if two surfaces are disconnected from one another, all of that will be caught by this check function. And so you see that there's a list of, I don't call them errors, but just problems with the model. And these problems are potentially going to cause meshing issues. And that's something that you need to keep in the front of your mind when you're using CAD Doctor is anytime that you spend in here, we need that to translate to some amount of time savings in the meshing. We don't just want to spend a whole lot of time here just to get the number of errors to go down. If we have a lower quality error, you can actually see that there's 3 levels of severity for these errors. We have critical errors, serious errors, and minor errors. If we have critical errors left over after after the completion of this healing process, then we might need to go back to our CAD system, or we might need to inspect these features a little bit closer. Serious errors, I don't really pay too close of attention to these anymore. I used to pay a lot more close attention to these because our mesher was less robust, but actually over the last maybe 2 or 3 versions of Moldex3D, our mesher has gotten to a point where serious errors most of the time are not an issue. And then minor errors are more of an indicator. They're not anything that I ever spend any sort of significant amount of time in fixing manually. Now, we just clicked on the check button. To the right of that is the auto stitch tool. The auto stitch is linked to a particular type of error called loop of free edges. Loop of free edges will happen whenever two surfaces are disconnected from one another, or if a surface is completely missing. In the first situation, the auto stitch tool helps us to stitch or merge those surfaces back together within a given tolerance. It's very possible that your CAD system had some tolerance for surface connection, and Moldex3D has a very different tolerance for surface connection. If the tolerance falls outside of the Moldex3D criteria, it's actually very possible that all of your surfaces are disconnected across your geometry, in which case you just need to use the auto stitch tool to merge those back together. Luckily, in this case, that is not the situation we've encountered, and actually that situation is pretty rare. But just know that if the auto stitch tool is available, you do want to use it. To the right of that is the auto heal function. The auto heal is going to attempt to take care of everything else besides the loop of free edges. So I'm going to hit auto heal. It's going to run through the healing kernel, and then it will actually go back and click the check button once again to update this list and tell us what has improved, what has changed from our original model that we brought into CAD Doctor. All right, so it looks like it took care of all the critical errors, all of the serious errors, and it's just left a couple of minor errors left over, which, like I said, I don't really go in and inspect these too closely. We can see the minor errors. If you highlight any of these categories, you can see an arrow pointing to where those problems actually are, so you can inspect them a little bit closer if you'd like to. But like I said, any sort of minor errors that show up here are not really necessary to look at too closely. All right, so those are the first three buttons. We have check, auto stitch, auto heal. And then the last button that we'll click here is export, which will bring us back over into Moldex3D Studio with our fixed model. Now, one thing that's really nice about CAD Doctor is it actually will never regenerate a surface automatically. If there's an error left over, that's usually because in order to fix that error, we would need to regenerate the surfaces on the parts. And regenerating the surfaces can mean that maybe the thickness changes. Maybe if I have to regenerate this curve here, maybe it becomes a corner instead of a big radius. And so CAD Doctor will never regenerate a surface for you automatically. And so you can have a high level of confidence that the geometry coming out of CAD Doctor is exactly the same as the geometry that went into CAD Doctor, just with some surfacing connection shored up. So maybe if there was a slight mismatch between where a corner is in the surface connection, or maybe if there was some small features that aren't necessary for the analysis, maybe it will shore those up a little bit.
Excuse me. Can you
All
let
right,
me
once we're
know
done with
what?
the fixed geometry function, you
Excuse
can
me.
exit out of this tab. You can either do that by hitting the exit button, or you can hit the X up on the tab itself. Either way, that will send us back to the model tab of the studio interface here. And like I said, we're just moving from left to right. You can see a lot of buttons are grayed out, and that's because it's waiting on this function specifically, which is the attribute function. Attribute allows us to tell Moldex3D what this object is supposed to do in the simulation. All right, so is this a part? Is this a runner, cooling system, insert? What is this object? When we import an object into Moldex3D, we don't tell Moldex3D what that object is supposed to do. The attribute is how we do that. All right, so I'm going to hit the attribute button. It's going to say select an object to edit attribute. So I'm going to select my part by left clicking on it. We'll see that the feature lines will turn from blue to yellow, indicating that the object is selected. And we'll see that the default attribution has been applied. That's a dark gray color indicates that this is an unattributed object. If I click on the attribute dropdown, we'll see all the different attributions that can be applied to this type of object. In this case, this is going to be a part, so I will change the attribute to part. We'll see that the color will change respectively. You see that it changes from that dark gray color to more of like a beige-ish yellow color. And actually, each attribution in Moldex3D has its own color associated with it. And so you can go down through this list and see what those different colors look like and what attributions receive which colors. You can actually change those color assignments up in your preferences menu, kind of like the mouse controls from earlier. All right, we can close out of the attribution function. All right, moving to the right of the attribute function is model thickness. Model thickness just quite literally gives us the thickness distribution across our part geometry. So after a small amount of loading the result, what it's going to do is it's going to find the distance between the top surface and the bottom surface of the part, or the inside surface and the outside surface, however you want to consider it. And it's going to give us a distribution accordingly. Now in Moldex3D 2025, a really nice added feature is the ability to change your units on the fly. And so you can actually see that my units over here are in meters, which I don't want. So I'm actually going to change my units to millimeters, which that should be the default unit system, is the metric in CGS units. However, if you wanted to change those units on the fly, if you're more of a English units kind of person, then you can use inches, whatever units you want here. You can edit those on the fly. And this applies to any result in Moldex3D, as we're going to see later. You can modify pressure units, you can modify distance units, all of these sorts of things you can modify on the fly in 2025, which is pretty cool. Now, if I want to figure out what the actual thickness is at a location on my parts, usually I'm just going to modify my scale. I can do that by left-click dragging the top of the scale and dragging it downwards. Right, and we can get a feel for how thick the different features are by when that surface disappears. So we can see that surface disappears around 3 millimeters, which is the maximum as I have it shown here. If I move my scale down a little bit further, all right, we see that the nominal thickness is somewhere around 2.5 millimeters. And it looks like there's some other features that are a little bit thinner, but that's how you can get a good feel for what your thickness distribution looks like. This could indicate maybe where you want to place your gate on your part. This could indicate where you might have some flow leading. All of these sorts of things you can identify through the model thickness before you run the simulation, but the simulation will tell you if ultimately this thickness variation will cause any sort of defects on the geometry. All right, now you can have this thickness distribution overlaid throughout the rest of your modeling process. However, I tend to not like the color distribution overlay just because it's a little bit distracting. So if you want to get rid of the thickness distribution, you can go back to the project tree, which over on the left side of your screen, you'll see 5 tabs up at the top left. You can click on the first of those 5 tabs to go back to the project tree. We're currently in the thickness distribution. If you click on model, that will get rid of the thickness color profile. All right, so that's the import and analysis section of the model tab. Now moving to the right of the import and analysis section is the runner system. So we've inspected our part, we have fixed our part, and so now we can place a gate on our part. Now there's a bunch of different ways that and a bunch of different options you have for gating. If you click on the drop down where it says gate here, you can see all the different options we have available to us, things like pin gates, edge gates, sub gates, fan gates, film gates. There's a lot of options you have here. And we also have an automatic gating function called the Gate Location Advisor. I won't be using it here just for time's sake, but I do have a video up on our YouTube channel that goes through the Gate Location Advisor in pretty good detail. So you can head over there to get a feel for what the capabilities of this function are and how it can help you to automatically place a gate based on your geometry. In this case, though, I will use the add pin gate function. And how this is going to work is I'm going to hover over the location on my part where I want a gate, left click, and it will place a gate normal to the surface that I clicked on. The default size of the gate that was created here was actually determined by the thickness profile and the volume of the geometry that I've attributed. And you do have the power to edit the size of this gate using the gate parameter over here. Now for a pin gate, the 3 dimensions that are necessary for the parameterization are the bottom diameter of the gate, the top diameter of the gate, and the length of the gate. In the add pin gate function, those are actually parametrically bound. However, once I get out of this function, they are not going to be parametrically bound. You can change each of those functions independent of one another, or each of those parameters independent of one another. All right, so if I change my gate number, let's say I change this to 1, you'll see that the shape and the scaling of the gate is, the shape of the gate is the same. It's just scaled down based on the new value that I've input here. The default is actually a pretty good value to start with most of the time. You can edit this value if you'd like to, but I'm going to just use the default. You can press the green check mark, and that will exit you out of the gate function. Now, I do have a third object that was created automatically by the add pin gate function, but if you just use the pin gate function, you might not see this red arrow on the top of your gate. This red arrow is extremely important to the analysis. This is what we call the melt entrance. This is going to be the starting point for our flow analysis, and you'll need to make sure that this is applied. If you don't have this red arrow, you can hit the melt entrance function, and that will help you to put the melt entrance arrow on top of the gate. So if your situation looks like this, you can hit the melt entrance button, and that will place that arrow for you automatically. And this isn't only done for simple systems like this. If I have a multi-cavity system with an extremely complex runner, you can still use this automatic melt entrance function. And it's actually really smart at being able to figure out where the open end of your runner system is and where it should be putting the melt entrance arrow. Now, on top of this gate, I could be putting the runner. However, the runner is a little bit more complex than we have time for right now. You can feel free to play around with this if you'd like. However, I will be foregoing that and we'll just use a gate in this analysis. Now, if I just wanted to run a filling and packing analysis, this is actually all of the information I need. I just need a part, a gate, and a melt entrance. Those are the three objects that I need to be able to run an analysis. Actually, technically speaking, I could just put the melt entrance directly on the part, but for visual confirmation of where the gate is, it's usually best to put a gate object there just for visual. However, if I want to go any further than the packing analysis, if I want to include warpage into my simulation, you need to include a cooling system. And I see a lot of our users will go through and they'll run an analysis for warpage without a cooling system. What that does is it assumes that there's a perfectly uniform temperature distribution across your part surface. And we all know from molding that is never the case. You have some sort of distribution across your part surface. That distribution of temperature is one of the primary contributors to warpage, and we are completely neglecting that if we don't include a cooling system. Even if you're upstream in the design process, you can create what we call a dummy cooling system, and that will be a stand-in for the heat transfer effect, or at least the heat accumulation effect in your mold, and you can study where improvements to the cooling system could lie, or maybe just get a feel for what the trend of warpage should be based on this differential temperature effect. This will be much more realistic than just having the part and the gate and the melt entrance. All right, so moving on from the runner system to the right is our cooling system section. We'll start off here with the mold base. All right, now the mold base is just going to be a box, and we're placing that box around our part and giving ourselves a little bit of extra room so that we can introduce a cooling system. Now the default parting direction was applied automatically based on my gate direction. And so it automatically knows to use the x-axis. Actually, by default, if I didn't include a gate before using the mold base function, it would use the z-axis. That is the primary default in Moldex3D. However, it automatically recognized to use the x-axis because of our gate direction. You can modify the cross-section parameters of this mold. You can see the L and W parameters. Those are the cross-section dimensions of our mold. We can edit those and get a live update. And you also have access to the height dimension as well. If you hit the blue arrow up here at the top of the mold base wizard, you'll have access to the overall height. And then you also have access to the cavity and core height dimensions as well if you wanted to modify the upper and lower sections of your mold. I do want to make a very important distinction though, and that is that the mold base that we're creating here is going to be one continuous box. All right, there is no separation between the cavity side of the mold and the core side of the mold. From a thermal standpoint, there is a contact heat transfer that will occur between those two halves of the mold. However, it's a valid assumption to just assume that they are continuous. We've done a lot of studies with discontinuous mold halves, and we found that the results do not change in a significant manner. And so actually this dimensions or this parameterization that we use here is just to modify the upper and lower sections of your mold. The parting line, quote unquote, that goes through this red line that goes through your part is actually just going through the centroid of the part perpendicular to the parting direction. And this parting line will actually disappear after the mold is established. And to do that, we're just going to go ahead and press the green check mark. the default size of the mold base. If you didn't change anything, that is perfectly fine. The default size of the mold base is plenty of room to give us enough space to design our cooling system. If you make the mold a little bit too large, that is actually not the end of the world. It'll add a little bit of computation time, but actually the effect of computation time is pretty negligible with respect to the size of the mold. So if you made the mold a little bit too large, that is perfectly fine. All right, so again, we're just moving from left to right across the interface here. So to the right of the mold base function is cooling channel. This will allow us to create our dummy cooling setup. All right, so we created our mold base. That's a great medium for heat transfer. But now we actually need the heat sinks, the cooling channels, to be implemented into our mold. When I go into this cooling channel function, it's going to put a bunch of cooling channels along the top side of our part and the bottom side of our part. Those cooling channels are controlled by 5 dimensions, or 5 parameters, I should say. The first of which is the channel direction, which you'll actually see that the parting direction is grayed out here. So you'll only be able to assign the non-parting axes as your cooling direction. Below that are your diameter. The D is the diameter of the cooling channels. If I increase this, you'll see that the diameter increases a little bit. N is the number of cooling channels on the top and bottom. So we have 14 along the top, 14 along the bottom, and I can change that accordingly. C is the distance between the cooling channels, something we call the cooling channel pitch. And you can increase this. I usually like to make sure that the cooling channels are spread all the way across my part so that they aren't localized to the center. We want a nice, even cooling distribution. Even if it is a stand-in for a cooling system, we still want it to be as reasonable and as realistic as we possibly can. Okay. By default, when you go into the cooling channel function, the number of cooling channels is going to be created such that they are spread over the entire surface. But if you reduce the number like I just did, then you will need to increase the spacing between those cooling channels so that they cover the entire part. All right, and then the last dimension here is actually the most important one. That is the height dimension. H controls the distance from your cooling channels to the uppermost or lowermost surface on your geometry. And the reason this is so important is if I have a cooling channel system like this, I'm going to get a localized cooling effect where this cooling channel proximity to the part is pretty close. Whereas in this area here, maybe the distance to the cooling channel is a lot further. And so I might end up getting this sort of like rippling of temperature across my surface, and that will introduce another variable into the analysis. So we actually prefer to push these cooling channels a little bit further away from the surface of the part so that we can eliminate that effect from this dummy cooling system or this stand-in cooling system. My recommendation is to set the height dimension as 10 times the default diameter. The default diameter here is 8, and so my height dimension is going to be 80. That will push the cooling channels far enough away from the surface of my part where the cooling channels can act as a singular heat sink rather than as individual cooling channels. All right, I'm going to press the green check mark to get out of the cooling channel wizard. And as far as the setup of this modeling goes, that's pretty much it. It's really easy to import the model into Moldex3D. Checking it through CAD Doctor is heavily recommended so that we can get as clean of a mesh as possible on this model that you spent so much time in CAD on. Then we can introduce the gate and the runner system from gate to gate. If there's a multi-cavity system, or if you have multiple gates on the same part, you can introduce a runner system in Moldex3D. Or if you want to, you can import your runner system from your CAD geometry or from your mold, and you'll be able to work with that the same way that we've worked with the gate here. And the same thing actually follows suit for the cooling channels. And the cooling channels are just a series of lines. You can import these lines from your mold directly if you're able to extract those center lines. You can import those directly, or you can use the CAD geometry directly from your mold and import those into Moldex3D. All right, the next step here is going to be meshing. But before we get into meshing, we're going to take a short break so everybody can reset a little bit, get up, walk around, and we'll come back in 5 minutes so that we can start covering meshing and all of the other simulation setup in Moldex3D before we move on to the result interpretation at the end of this session. All right, welcome back, everyone. So the second hour here, we're going to go through meshing theory and the rest of the setting up of the simulation. We've gone through the modeling already, so we'll go through the meshing part, followed by material selection, as well as process setup. All right, so now that we have all of our components, which are the part, the gate, our cooling channels, and the mold base, now we can go through and mesh this entire geometry. To do so, we're actually going to go over to the mesh tab, and we'll have to do that manually. This is pretty much the only step that we have to do manually, just because there's different situations where you would want to go over to the mesh tab. If I'm only running filling and packing, maybe I don't need a cooling system. Once I run a cooling system, maybe there's some checking functions and so on. But we'll go over to the mesh tab, and once again, we'll move from left to right. The first button here, actually, you don't have to interact with. This is more of just a reminder of the meshing type that you selected when you were back in the home tab. If you remember, you selected your mesh type here. So this is just a reminder for what that mesh type is. To the right of that is what we call the node seeding. Now, when we mesh in Moldex3D, it's very important to note that there's two different types of meshes that are going to be created. The first mesh is going to be the surface mesh. This is going to go across the surface of your geometry, and we're going to convert your solid model into a series of surfaces, and then we're going to convert those surfaces into a series of surface meshes, which are going to be a series of triangles. If you've ever seen a mesh from Moldex3D before, you'll know that there's a bunch of triangles that are going to be across the part. That's your surface mesh. From that surface mesh, we're going to create a solid mesh through the thickness of our part. This is what we call the boundary layer mesh, and is the second type of mesh that will be created. The seeding function allows us to set up the template of our surface mesh. The surface mesh is going to be, like I said, the series of triangles. And we need to determine what the size of those triangles is going to be to optimize our solver performance and the approximation of the geometry with respect to how we create these triangular surface mesh elements. All right, so I'm going to go into the seeding function. It's going to ask me to select a polysurface, which a polysurface is just a fancy term for a solid geometry. So we'll go ahead and select the part, press the green check mark, and it'll isolate that object from the rest of my model. Now, if I hit apply here, it will create the nodal structure across my geometry, and you'll see that these black nodes are going to be placed along the feature lines of my part. The number of nodes and the spacing of these nodes is going to be determined by the singular parameter that you have access to, which is the mesh size parameter. The distance between these nodes, the nominal distance, is actually as an average would be this value in your current unit system. So in my case, I'm in millimeters. So here, these would be nominally about 3.176 millimeters apart from one another. If I increase this value, let's say I go up to a value of 10, the spacing between the nodes, I'll hit apply. The spacing between the nodes will increase, and therefore the number of nodes across my geometry will decrease. And the inverse would happen if I decrease the value. So if I go down to a mesh size of 1 and hit apply, we'll see that a lot of nodes are placed across my geometry because the spacing decreased. Now, the value that you use for node seeding is going to be something that you'll need to optimize. From the simulation side, we would prefer to have a high number of elements because that will allow us to capture the results in high resolution. And in addition to that, I'll be able to capture some of the features across my geometry in pretty good resolution as well. For example, if I flip down to the bottom side of my part and I zoom into these bosses, with a mesh size of 1, we can see that the number of nodes around the circumference of this boss is pretty good. But if I go back to the default, which was something like 3, and hit apply, we can see that the number of nodes around the circumference decreases pretty drastically. We have 1, 2, 3, 4, 5, 6 nodes around the circumference, which means that when we go to create a surface mesh, this is actually going to become a hexagon. And that's not a very good approximation. What we're going to do is we're going to optimize the number of nodes with the number of features across our geometry. And to do that, there's a specific methodology that we call the Goldilocks node seeding. The Goldilocks node seeding, and we're going to have to rotate to a very specific viewport, and then we're going to specify our node seeding based on the nominal distance between those nodes. So first of all, we're going to rotate our part so that we're looking down in the parting direction. Second of all, we're going to rotate our part so that the longest dimension is horizontal on our screen. And then lastly, we're going to zoom in so that the part fills up our entire modeling window. What this does is it normalizes the size of the part to our computer screen, and so that we can use the nominal distance between the nodes as a marker for what size we should be applying. Generally speaking, I want there to be about 2 to 3 nodes width of space in between these black nodes. You can see that each of these nodes has a width to it. You can see that each of these black nodes has a width to it. I want to be able to fit about 2 to 3 of those black nodes in the space between the black nodes. So you can see right now, I can fit about 1 node in the space between those black nodes. If I increase this value, let's say I go up to 5 and hit apply, we can see that more nodes can fit in that space. I can actually get about 2, maybe closer to 3 nodes in that space. So I would say that this node seating for this part is pretty good. All right, so node seating of 5 is what I would use for this part geometry. Now I mentioned the geometry the geometry approximation aspect and the simulation aspect of node seating, but what's stopping us from going smaller in our mesh size? And that's going to be computation time. Now I can make the node seating go as small as I want to, but that's going to drastically or very quickly increase my element count. And that increase in element count is ultimately going to be a contributor to the simulation time that I get as an output from Moldex3D. All right, and so I can't just decrease my mesh size too much because then my element count is going to get high, and especially if I have a large number of iterations that I need to run, my simulation time is going to start increasing exponentially. All right, so I'm going to press the green check mark to get out of this section of the node seating. This is what we call the global node seating. Now, if there's any features that I want to shore up, or if there's any features that I want to have a higher resolution, like I can see down on these bosses, and I mentioned this earlier, if I use a higher node seating, then we only get 6 nodes around the circumference of the inner circumference of this boss, and even actually with this higher node seating, the outer circumference of this boss. So if I want to approximate this a little bit better, then I simply just need to go in and increase the number of nodes for this feature specifically. I don't need to increase the global node seating just to increase the resolution of mesh along this feature. I can use this secondary section of the node seating to do that. And that's what we call manual node seating. Quite obvious. There's 2 ways that we can apply a manual node seating. The first one is through the number of segments. For example, if I wanted to click on one feature line and I wanted to change the number of segments along that feature line, you can see right now it is 3, which is 1, 2, 3. If I wanted to increase that to, let's say, 5, I could do so. However, generally speaking, I'm going to box select an entire feature, which includes a lot of different lengths of feature lines. So if I use the number of segments, it's kind of difficult to get each feature line to have the same node seating if the segment length is different. And so in that situation, I'm going to use the other option, which is mesh size. So instead of using the nominal node seating that I used across my part, which remember was 5, I can use a different node seating for this feature specifically. Maybe I'll use a mesh size of 1 for these selected feature lines. To select a group of feature lines, you can simply just left-click drag a box. That will allow you to select those lines pretty easily. You don't have to select them one by one. That would take forever, and we wouldn't want you to do that. All right, so you can just left-click drag, and that will select all those feature lines for you. All right, I'm going to leave the other 2 unseated just so you can see the contrast between the higher resolution mesh and the lower resolution mesh. But if you want to change all 3 of them, feel free to do so with a little bit of practice. I'll say most of the time, I actually do want my node seating to be as uniform across my part as possible. And so I don't spend too much time or effort to go in and manually seed certain features just because I want this average mesh size to be applied so that I'm not introducing another variable into my analysis. But smaller features like this, and especially features that I'm going to be measuring as an output from Moldex3D, these important features, we do want to be a little bit higher resolution, just so we can get a higher nodal count there. For example, for roundness, we use the number of nodes around the circumference. For distance measurements, maybe the number of nodes can increase the possibility that the nodal representation is in the place that you want it to be. These sorts of things can be improved with a higher node seating. But generally speaking, we like to keep the node seating as uniform as possible. Once I've applied that node seating, we can go ahead and press the green check mark. And that will return us back to where we were in the mesh tab, and it'll bring back the rest of our model. And that sets up the template for the first type of mesh that we're going to generate, which is the surface mesh. Now, to the right of seating is generate, but before we go into generate, I do want to establish the parameterization for the solid mesh. And before we go into these too far into what the parameters we should be using for that, we can go into the parameter function, which is where we're going to apply the parameterization for the boundary layer mesh. But I want to explain a little bit more about how the boundary layer meshing works in Moldex3D, so you can get a feel for why we use the parameters that we do. And if you want to change these parameters in the future, which parameters should you be using for which purpose? I think that's really important to know. All right, so in Moldex3D boundary layer meshing, what we have here is just the top and bottom bound of the part. You can consider this the top and bottom of your part, or the left and right surface, or the front and back surface. Every area of your geometry, in order for it to be considered a closed volume, needs to have two bounds. What we just did in the node seating was we applied nodes along the top side and the bottom side in a nice, evenly structured manner. And that's going to create a bunch of surface mesh elements on the top surface and on the bottom surface. So what we're doing here is we're looking through the thickness of our part. In the boundary layer meshing technology, what we're going to do is extrude these nodes from the top side downwards and extrude the nodes from the bottom side upwards to create a 3-layer structure that looks something like this. The upper and lower layers are what we call the boundary layers. The middle layer here is the tetra layer. The tetra layer actually just serves as a connector between the two boundary layers. And actually, the boundary layers are where we're going to be calculating a lot of the important information as it pertains to plastics molding. Now, if I ran the simulation like this, where I have just 3 layers, there isn't really enough resolution to get the quality of results that we want as an output from the simulation. And so instead of just using a singular extrusion like this, we subdivide that extrusion into a series of layers. This right here is what we would refer to as a 5-layer boundary layer mesh. So we have 5 layers on the top, 5 layers on the bottom, and at least 1 layer of tetrahedral elements through the thickness. Now, once this subdivision is created, now we can create the tetra layer, which is pretty much just a connector between these two boundary layers. Actually, in an ideal world, I'd be able to extrude the nodes all the way from the top surface down to the bottom, because the element quality would be better that way. But because we can't ever guarantee that the nodal structure on the bottom surface is the same as the nodal structure on the top surface. Maybe if there's like logos or ribs or bosses, like we saw in the part that we're working with, there's no way to guarantee that the nodal structure on the bottom is the same as the nodal structure on the top. And so we need this connector layer to act like glue between these two structured layers. Now, I mentioned that the boundary layer section would be higher quality element than the tetra layer. So let's take a look at the different element types that exist in Moldex3D. The first one is called the tetrahedral element. You might have seen these if you've used FEA or any sort of structural type of analysis. These tetrahedral elements get a lot of their strength from their flexibility. So for high deformation cases, for complex geometries, tetrahedral elements are really nice in being able to, you can move each of these nodes independently without necessarily impacting the other nodes. And so deforming mesh, having flexible meshing, these are very good for that type of application, which actually, as it turns out, is really good for the tetra layer in the middle of our boundary layers in the case that the boundary layers have some weird structure to them. Now, in the boundary layer sections, we have what's called a prism type element. The prism type element is effectively just an extruded triangle, because that's exactly what it is. We have a triangular surface mesh element, which we'll see in just a moment when we go to mesh this. And then that surface mesh is going to be extruded downwards to create this boundary layer section. And so these are the elements that will exist there. The third type of element that we'll see in Moldex3D doesn't exist in the boundary layer type of meshing method, but we will see it in the meshing style or the model that we've selected. The hexahedral mesh is effectively like two prism elements put together. And when we start looking at the quality of elements, this is going to be linked to the number of nodes that exists on that element type. For example, a tetrahedral element has 4 nodes, 1, 2, 3, 4. When we're running the analysis, actually the computation is being done on the nodes themselves. And in the color distribution that you see as a result in Moldex3D is an interpolation of those nodes to some point in the middle of this element. The more nodes you have, the more interpolation points there are, the higher the precision of the analysis. And so a prism element you can see has 6 nodes, a hexahedral element has 8 nodes. And so actually a hexahedral element is the highest quality element available in Moldex3D, followed by Prism, followed by Tetra. And this doesn't only apply to Moldex3D simulation, this actually applies across the board in simulation. Hexahedral elements are the highest quality type of element that are currently available. All right, so what does that look like as far as the results go? So if we have a boundary layer mesh structure that looks something like this, the injection molding velocity profile, hopefully we all know that we're using fountain flow. And this is a parabolic velocity profile where the velocity is pretty much 0 at the mold surface, and the velocity is at its maximum at the apex of this parabolic curve. Which actually, as it turns out, the maximum velocity usually occurs in the tetra layer. So you might think, Alex, okay, well, is the tetra a lot more important than the boundary layer? My answer to that is not really. Actually, if I draw an arrow down to the boundary of the tetra layer, we can see that the change in velocity across that layer is quite minimal. And this doesn't only apply to velocity, things like temperature, shear, fiber orientation, even to some degree. We can see this effect quite a bit where the change in the result is not that significant in the tetra section of our mesh. And so that brings up a very important note about simulation. Actually, the maximum velocity here is just a number. What we care about as far as the accuracy and the precision of the analysis is the gradient of the results. Where there is a high amount of change in the results, that is where we want a higher quality mesh. And so we can see in this first element layer, closest to the mold surface, we can see a huge change in the velocity profile, and that diminishes as we get closer to the center of the part, and obviously symmetric on the opposite side. And that's why we are okay with using this boundary layer mesh structure, as long as we're able to capture a large majority of this gradient in the higher quality meshing section. We're okay with having this tetra layer in the middle to act as glue between the two higher quality mesh regions. And that brings up an important point, and that is what we call the offset ratio. Now, if I pop back over to the interface real quick, once again, I'm over in the parameter section of the mesh tab to see all these solid mesh parameters. And in the geometry meshing section of the result tab, I'm sorry, of the solid mesh parameters, I'm going to set my attribute as part. You can see a couple of different attributions under here. The mesh type actually corresponds to how many layers you want through the thickness. In the example that I just gave, this would be a 5-layer BLM. We have 5 layers on the top, 5 layers on the bottom, and then 1 layer of tetra through the middle. So that would be a 5 layers BLM. This is actually the maximum number of layers that you can create by default, but as you can see in my interface here, you can go a little bit higher if you want. But we found that anything higher than 5 layers is just a diminishing returns, kind of like with the node seeding that I mentioned earlier. If we increase the number of layers, that increases the element count, which will increase your simulation time. And if there isn't a good amount of benefit from that added simulation time, then it's pretty much just a waste. So we've done a lot of studies with the number of layers through the thickness to figure out that 5 layers BLM is the ideal number. Now, the other parameter that you have available to you is what we call the boundary layer offset ratio. So I want to explain this in a little bit more detail as far as how this works with respect to the mesh. All right, so the boundary layer offset ratio is governed by this equation where T equals S times OR, where T is the offset distance or the extrusion distance of this boundary layer section. S is the node seating, or the distance between the nodes here. And then OR is this scalar offset ratio parameter that shows up in the interface. If I were to rearrange this equation, the boundary layer offset ratio is a ratio between the extrusion distance and the node seating. So if I had a boundary layer offset ratio of 1, it means that my boundary layer offset distance is equal to my mesh edge length, just as an example. What that means visually, though, if I have a low offset ratio, that means my boundary layer offset distance is smaller. And if my boundary layer offset distance is smaller, then that extra space has to be compensated by the tetra layer. That means the tetra layer is going to become more and more dominant through the thickness. And that's something that we want to avoid. One, because the structure of the boundary layer mesh is such that the results have a little bit higher precision. And like I just mentioned, the element quality of the boundary layer section is higher than the tetrahedral elements in general. So we want to avoid having too thick of a tetra layer. On the opposite side, though, if I have my offset ratio too high, theoretically, I could get a situation where the two boundary layers overlap one another, which this is also a bad situation. We wouldn't be able to run a simulation where two elements occupy the same uh, area in the part. This actually used to be a huge thing that we would have to go through and adjust, but luckily now the algorithm that we've implemented in our boundary layer meshing solver is such that if an overlapping mesh condition occurs, we'll dial back the offset ratio gradually until there's a minimum tetra layer that's created in the thickness. And as it turns out, that is actually exactly what we want. We want the tetra layer to be as small as possible, still good quality, but we want it to be as thin as possible so that the boundary layer sections can dominate as far as the results are concerned. And so these actually end up pairing pretty well with one another. And so in the interface here, I'm just going to set my boundary layer offset ratio as high as possible. And then I'm going to let the algorithm in the background determine what that actual offset ratio should be so that there's no overlap. If I set a really high offset ratio, let's say I have an offset ratio of 10, you'll see the actual constraints come up. The offset ratio should be between 0.1 and 3.0. And so I'll just set to the maximum here, which is 3.0. And that is the value I will use for every mesh that I run in Moldex3D. It doesn't matter the application, doesn't matter the situation. I will always use a boundary layer offset ratio of 3.0 for the parts. Now down below that is the curve meshing section. There's actually two types of objects that we have in our modeling. We have the part, which is a polysurface object, and then we have the runner and the cooling channels, which are actually line-defined objects. If I zoom in on this object here, you'll actually see that there's a center line going through the middle of my runner, and you'll see the same thing with the cooling channels. You don't have to do this part, but if I were to unattribute the cooling channel, you'll actually see that it is just a line. Like I was mentioning, you can draw the center lines in your CAD system and import those, attribute those as cooling channels, and you'd be good to go. So this curved meshing style here is for these line-defined type objects. What we're going to do is we're going to create a two-dimensional array of mesh, kind of like a surface mesh. And then we would extrude that two-dimensional template to give us our 3D solid mesh. Actually, as you can see here in this template, and this is actually the template that we will use for the runner, in this template, all of the elements are quadrilateral by nature. And so when we extrude these quadrilateral elements, that will create a hexahedral type of mesh for our runner. And the same thing will actually apply to our cooling channels. The cooling channels you can see also have that quadrilateral mesh array here. And so when I paste this onto the entrance of the cooling channel and extrude it, I end up getting a very high quality hexahedral mesh out of it. Actually, you don't have to change either of these. The default style for the runner and the cooling channels are perfect. However, you do have the option to modify them if you so desire. For example, the cooling channels, if I wanted to do like a CFD study, maybe I would want some more layers closer to the mold surface or to the outside of the cooling channel, and therefore I could increase my number of outer layers. You can see that the template will update accordingly. But to optimize the element count, once again, we need to consider not only the resolution and the precision of our analysis, we also need to consider how long it takes to get those results. And so to optimize the element count, 3 layers and the outer is perfectly fine for most analyses. Just for some, you might need to increase that layer count. Okay, once we have all of the solid mesh parameters set up, we can go in and generate our mesh. So I'm going to go ahead and hit generate. And when you hit generate, you'll see the structure or the sequence of meshing that we use for Moldex3D. So we're going to generate the surface mesh of all of our polysurface objects, which in this case is just our parts. Then we have the solid mesh of our parts, the solid mesh of our runner, so that's our melt system, and then we have the solid mesh of our cooling channel and the solid mesh of our mold base. If you wanted to stop the mesher at any point, you can place attack by just left clicking on that section, and it'll stop the mesher at that point, so you can maybe inspect the mesh or take a look at the part or whatever you want to do. But if you just wanted to run the mesher all the way through, you can hit generate, and it'll generate the mesh, no problem. All right, so I'll just kind of show you what's going on here. So we have the surface mesh of our parts. You can see all the triangular surface mesh elements that are created automatically. You can see that it refines around some of the smaller features on our geometry. Down on the bottom, you can see where I increase the node seating. You can see that there's more nodes and a lower node seating over there versus something like this. You can see that hexagon created in the middle of this boss. Then on the top side of our part, our runner, you can see that hexahedral style. You can see that two-dimensional template extruded, and then it's also matched to our part surface. That creates a nice continuous flow calculation from the runner system all the way from the melt entrance all the way to the end of fill in our parts. The cooling channels will also have this hexahedral array. They don't have to match to anything, which makes them really quite simplistic as far as the generation of the mesh is concerned. You can see that two-dimensional template, and then it is extruded all the way along the line. And then finally, the solid mesh of the mold base is created. That solid mesh of the mold base matches to all of the other components of our mold, things like the part, runner, and cooling channels, any inserts that you've brought in, all of these things the mold base will attempt to match to. And then once all of the mesh has been created, you can go ahead and hit final check. This final check will save the mesh in 2 different formats, actually. It'll save the mesh in the editable format, so you can actually go back and forth. This actually enables you to maybe go back and change your gate location or change your cooling layout or whatever you want. And then it'll also save the simulation ready mesh file so that you can actually go in and run the analysis. The biggest thing to note here is that if you don't final check, you won't be able to move on in setting up your simulation. So it's very important that you make sure that you hit final check. And once you final check and press OK here in this, when it says mesh is ready for analysis, if you press OK, it's actually going to push you back over from the mesh tab to the home tab. And then we can continue on in the home tab from where we left off. So if you remember, we clicked on the import geometry. So now I can go through and start to look at some of the different input or the other inputs into the simulation besides the model, which are the material and process pretty much. Now for selecting the material, we have an entire public database that you have access to. If you click on the material button, that'll bring you to the material tree, and you can click where it says not specified to see all of the materials that you might have used recently. If you don't have any recently used materials, like kind of like what I'm showing here, then you can either import a material if you already have that access to that file, or you can open up the material wizard, which is where our public database is located. I'm not going to go into too much detail as far as the material properties here, just for time's sake. But you do have access to things like viscosity, PVT, specific heat, and we're very transparent about the numerical models that we use. If you go up to the top right corner of any material that you find in Moldex3D, you can access the numerical model that we use, find some of the constituent equations and what we're fitting all of these material characterizations to. But in order to find a material file, you'll go over into the Moldex3D bank. This is our public database. And the public database here is sorted by polymer type, then by manufacturer, and then by grade name. All right, you also have a search function over here where you can search for certain materials either by their polymer type, their whoever made them, and the grade name. You can search for any of those characteristics. You can also search for things like the type of filler. There's a lot of cool search criteria that we have here. Once you find the material, I'm just going to go to the first material that shows up here under ABSA Schulman. You can right click on that material and add to project. That will add the material file to your project tab. And that means when you close out of the material wizard, that material file will be loaded into your project automatically. Now, one thing I'd like to note as well is the existence of what we call the Material Hub Cloud, which is available on our Multiverse platform. If you've been around Moldex3D for the last year or so, you've seen that we've come out with this new online platform called the Multiverse, where we have a lot of cool functions and a lot of information at your disposal. Anyone who is current in their maintenance with Moldex3D has access to the Multiverse platform for free. You just have to set up an account. You can contact any Moldex3D representative to have your account set up for you. And in the multiverse, we have several functions. The first one is the university, where you can see a bunch of videos and tutorials and things like that to get started in using Moldex3D or to learn a little bit more about plastics molding in general. And we have a lot of useful information there. Below that is the Material Hub Cloud, or what we refer to as the MHC, which is what I'm going to show off here. And there's a couple of other functions that exist as well. University and the Material Hub Cloud are certainly the biggest two at the current moment, but we intend to add more and more functionality to this multiverse as this multiverse matures. Now, in the Material Hub Cloud, you can do a couple of things. We have a search function through our database. So this is the public database that you see in the Material Wizard. You have access to all of the properties that you would have access to there, in addition to a quality index. So each material, depending on where that data came from, will have a quality index assigned, which will tell you the relative quality of that material. So this one, for example, is yellow quality. A great quality material would be green, and a poor quality material would be red. We're going through our database and tightening up some of the tolerances that we use for the quality level. A lot of those lower quality materials are being removed from our database and replaced with either newer characterizations or other materials that have been tested for. And so actually from version to version, you might not see that the total number of material files increases. However, the quality of the average quality of the materials in our database will increase from version to version, and not even from major version to major version, like for example, the upgrade to 2025, even from 2025 R1 to R2 to R3 to R4, these are quarterly releases of Moldex3D. You'll see this improvement as well. And the nice thing is, because this is an online platform, we do update this live. You don't have to install the new version of Moldex3D in order to see this improvement. So you will see that newer materials will be added, even if you haven't installed the newest, latest version of Moldex3D, which is pretty cool. And I think the biggest benefit out of this MHC, I'm not going to go through the MHC in its entirety, but you can, we have a nice video up on our YouTube channel that goes through this and a lot of documentation for all of the features available in the multiverse. However, this one here is quite notable. This is the alternative material suggestion tool. So if you have a spec sheet for the material, but you don't have the characterization of the material, you can input some of the values that you see in that spec sheet. Things like your flowability, your density, maybe the recommended processing conditions, the type of filler, and so on and so forth. And this tool will output a similarity index for the materials that exist in our database. And then you can actually, from here, if I click on the triple dot, I can export or download this material file, and then I can import that directly into my simulation. So if you don't have the material, file available in the public database, you can search for a reasonable alternate to use as a stand-in for that material going forward. In addition to that, we do have the ability to create material files from a raw material testing. So you can send those materials to us. And we also have our own characterization lab as well. So we have over in our headquarters, which is located in Taiwan, we do have access to material characterization capabilities, not only for thermoplastics, but also thermosets. And we can test those for a nominal fee. You can also send these spec sheets directly to us. We can suggest an alternate. We can create material files like I just suggested. Both of those are free to you. Just the material characterization has a fee tied to it. All right, if you do have any additional questions about materials, you can send those into the chat section of Teams, and I'll help to answer those at the end of this training. But we'll move on for now over to the process. There's a lot of things to note in the process. I'm going to click on the drop down and go to New. You can import a process from a different project. You can also create a default process, which is determined based on the part geometry, the gate location, the material that we've selected, and a few other parameters along the way as well. So I'm going to hit New here, and that's going to open up the process wizard. All right, the processing methodology in Moldex3D is split into pretty much two camps. We have the CAE mode, and then we have machine mode. Now, machine mode is split into two sections, which is machine mode 1 and 2. We pretty much always use machine mode 1. It's pretty rare that we use machine mode 2. All right, so I'm going to start over in CAE mode, and then we'll move to machine mode 1 in just a moment. The primary difference between CAE mode and machine mode is how much information you have at your disposal. If I'm upstage or if I'm upfront in the design process, then maybe I don't have access to what machine I'm using. I don't have access to what parameters I should be using on the machine. And so CAE mode really helps to simplify a lot of these inputs so that it makes sense in the simulation world. And then the outputs from the simulation can be used to drive what the process engineers use to develop the process on the real molding machine. So CAE mode is a great option for those that want to run simulations upfront and then use the simulation results to drive the process in the future. Machine mode, on the other hand, will help us to correlate the real process data from the molding machine over into Moldex3D. You can already see that when you select machine mode 1 here, you actually do go in and select what machine you're using. That will create a parameter set for that machine. And then as we'll see in just a moment, the actual parameters used in the process are going to correlate directly to the molding machine rather than being a little bit more generic like in CAE mode. All right, so CAE mode, like I said, is used more upfront before production or before the process has been developed, before the machine has been selected. Once the machine is selected and once we have that processing data to go off of, machine mode helps us to correlate that data over into the simulation world. All right, so pretty much I'll say pre-production, we use CAE mode. Post-production, we use machine mode. That's the way you can think about it. All right, so as far as CAE mode is concerned, the only limit that we apply is the injection pressure limit. Most of the time when I'm running CAE mode, I will just use the kind of like the um, uh, a pretty high value, I'll say. I'll just use a really high value so I don't hit the limit. Most of the time when we're using CAE mode, we're not necessarily caring too much about what machine we're using. We want to know how much pressure is required to fill this part. And so if I limit that, then I don't actually know how high the pressure is going to get. And therefore I don't know what machine I'm ultimately going to need for the real molding process. All right, so usually I'll set this value pretty high, but this is the only limiter in the simulation. The rest of them over in the filling and packing tab are more of the exactifying process parameters. So we have things like the filling time. The filling time allows us to determine the fill speed. And it does that by, it already knows what the volume of fill is. We have our part plus runner volume. We already have our volume. We're inputting this fill time. And so the volume divided by fill time is our flow rate. It's going to use that as the I don't know, it's going to use that as the flow rate for the simulation. That's going to be a constant value in the injection molding process. We're using a constant flow rate. And so that's how it determines the flow rate here. The flow rate profile and injection pressure profile aren't too important. I'm not going to go through them here just for time's sake. VP switchover, you can use a couple of different values. You can either use a percent fill, which is pretty typical. You can also use a control point pressure. If you have a point in your part where you want it to switch over, you can do that. And then from the packing side, you can input the packing time, which would incorporate your pack plus hold, just as a small note. And then you can change what packing pressure you want to use through your pressure profile. Down below that is your processing temperatures. You have your melt temperature and your mold temperature. Melt temperature is going to be a homogeneous condition applied at the melt entrance. So just note that as the more you model, not only the gate, but for example, the runner, even the nozzle and the barrel, I see some users modeling all the way up to the barrel. The more information that you include in the analysis, the more of a realistic condition you have in the simulation. But kind of like what we mentioned in the mesh, the more information you include, the longer the simulation time is going to be. So there's kind of a trade-off there. All right, and actually the cooling is the same between these two processing methods. So I'm going to back up for just a moment so that we can look at machine mode 1. And like we saw before, in machine mode 1, we can select the machine. We actually have a database for all these machines. You see all the different machine manufacturers, things like Arberg, Fanuc, Engel, Sumitomo. You can see a lot of these different machine manufacturers here. Some of them have an M next to them, and some of them just have a kind of like a picture of a hopper and the screw. If we have an M next to the manufacturer, it means that we've worked with that manufacturer specifically to incorporate their interface into the Moldex3D process wizard. All right, so for example, if I use an Arberg machine, I'm just going to select a machine in Arberg and press OK. It'll ask me if I want to scale the profile settings. I'll click yes. And interestingly enough, you can actually see that it gives me a warning saying that the maximum shot volume is smaller than the parts volume. So it's indicating to me that this machine that I've selected is too small. It will give you these warnings and these messages to make sure that you're using the correct machine, the right type of machine, the right size of machine. These types of messages are very important to pay attention to in the setup of your process with machine mode. I'll press OK just to ignore that message. I wouldn't normally want to ignore that message, but I'll do so for now. And then because Arberg, we have worked with them to incorporate their machine interface, there's a checkbox down here at the bottom for machine interface. If I check that box and then hit next, we'll actually see that the machine interface for Arberg, the Sologica, I think is the name of it, the process screen here for Arberg will show up, and it is interactive. So I can go in and actually specify my process parameters on the interface itself. Note that only the process parameters that are necessary for Moldex3D are going to be available. And so there are some buttons that just won't do anything, but know that the buttons that are interactable are what are actually translating information from the interface over from the machine interface over into the process wizard. Now, regardless of whether you use the machine interface or not, you do have access to modify these parameters independently rather than using the interface, or the machine interface, I should say. And so we have access to things like the flow rate profile. You can modify your flow rate profile as a linear velocity of your RAM. You can also use a flow rate. You see all the different units and different specifications there. And you can also specify how much material you have before past your check ring, which would pretty much just be your your initial RAM position. All right, the output from the simulation will be your cushion. So the simulation isn't required to use all of the material that you've given it in this RAM position. You can actually see that this RAM position determines the injecting volume. If I change this to, let's say, 100, we see that we get a lower volume, went from 53 down to 49. And you can actually see that it gave me a message saying that the value is suggested to be larger than some amount so that we can actually fill our part. So it's taking into account the volume that our shot should be, and it's telling us that we will probably need more material. I can ignore that, it's just a warning, but if I do ignore that, then I do have the risk of short shotting in the analysis because I run out of material. That's a very possible scenario. All right, then like CIE mode, we also have the ability to change our VP switchover. However, there's an additional option you can actually set as the default. You can use the RAM position as a VP switchover. But like I said, just like in CIE mode, you can use volume percent fill. You can use a point control depending on how you're actually doing it in reality. And in packing pressure, you can see that you can set pretty much the same, as well as the processing temperatures. From the cooling side, you can set up your cooling time, your mold open time. These are two of the pretty much the most important parameters of the cooling stage, in addition to things like the coolant temperature, which you can use the cooling and heating button down here to access your the cooling channels that you've set up in your simulation. So you can see that I have 1, 2, 3, 4, 5, 6, 7, 8 cooling channels along the top and probably 8 along the bottom. And so I should have 16 channels total. And so you can actually go in and modify what temperature you want each of these channels to be. So if you wanted a different core temperatures versus your cavity, and if you have two different thermometers set up on your mold, then you can go in and change, or you can make a variable temperature layout like that. In addition to that, you can change your mold metal material. By default, it's always going to be P20, but you can change this to be whatever you want to. And we have a whole list of materials, and we add to this list every year or every version. You can see things like P20 is the default, like I mentioned, F7, H13, stainless steel. You can really choose anything under here. Mold Max for inserts. There's a lot of interesting material properties that you have at your disposal. And we can create materials for you as well. They're pretty simple, actually, to create a mold metal material. You just need these 6 parameters: density, heat capacity, thermal conductivity, and some of the mechanical properties. All right, if I hit next, we get an estimation of our cycle time. That's the only real notable thing in this list besides just all the number inputs that you had in the previous tabs. But the cycle time is an addition of your filling, packing, cooling, and mold open times. And so the output of the simulation will tell you if that 30 seconds, like we have in this case, if that 30 seconds is sufficient for this part. You'll be able to interpret that. All right, I'll hit finish here to save my process file. Okay. And that will enable the rest of the functionality in Moldex3D, or until I run at least. To the right, remember we're still just moving from left to right across the interface. I can't emphasize that enough. Is how fluid the interface is when you just follow it from left to right. Don't be skipping all over the place. To the right of the process is the analysis dropdown. This is where we select what analysis sequence we want to use. If I just want to see the filling properties, if I just want to see like the shear in my part, if I want to see the pressure loss through my geometry, I can just run a filling analysis. If I want to see the effects of packing, if I want to see maybe the final part weight, or if I want to see how much packing time is going to be required for this, if I want to try out different packing profiles, then you can use a filling and packing type analysis. And if you want to run warpage, there's the sequence here. Transient analysis is the type of analysis you would want to use for your simulation. In this case, I would select the transient analysis for a warpage analysis. To the right of that is computation. I'm not going to go into computation too much here, just for time's sake, but we do have a good amount of information on the Multiverse as well as on our YouTube channel that goes over some of the computation parameters. So you can head over there to get a feel for that. And to the right of that is run. Now, I've already pre-run this simulation, so we don't have to run the simulation over the short break that we're going to have going into the third section. But if you'd like to run the analysis after the training is concluded, then feel free to do so. It should run in about, this sequence should run in about 2 to 3 hours, I would say. Yeah. All right, that being said, we're going to take a short break. We'll take another 5-minute break. And when we come back, we'll start talking about the analysis results. What happens after we've run the analysis? Can we interpret anything meaningful out of the analysis that we've ran? I certainly hope so, and we'll figure out how that works after the short break. We'll see you in 5 minutes. All right, so going into the last section here, we're going to go over the result interpretation of a simulation ran in Moldex3D, particularly a warpage result simulation that was ran in Moldex3D on the part that we've been using this entire time. To open up that simulation file, you can actually keep the interface open for the project that you've been running, but I'm going to minimize that for the time being, and I'm going to go into the project folder. So I'm going to open up that consumer folder. And in that consumer folder, you'll see a series of subfolders. If you remember, we actually went to the CAD data folder earlier to find the step file. But actually, if I go down a little bit, there's an MRM file here. You can actually double click on the MRM file to open up the project straight away. You can do this for any project that you create in Moldex3D. The folder structure will be exactly the same, regardless of what regardless of what application you're using or anything like that. The file structure will be the same, and the MRM file will be there to open up Studio at your convenience. You could also open up the Studio window and then use the Open option. If you remember at the beginning of this training, we used New to create a new project. You could use Open to also open an existing simulation project as well. But this, in my opinion, is the shorter and more efficient way to go about it. All right, so when we open up a pre-ran simulation, we're going to have access to all of that information over in the project tree on the left side of our screen. All right, so we see all of the inputs, things like the material, process, the model. I can go to my thickness distribution if we want to look at that again. And then below that is the result item. So we see filling, packing, cooling, and warpage. I'm going to go through all four of those in sequence. So we're going to start in the filling results. All right, the first thing that shows up when I go into my filling results is the melt front time. And this is a Premiere result. You've probably already seen the melt front time quite a bit if you've seen simulation at all. The results, you'll usually see the melt front time, but actually you'll usually see it as an animation rather than the color distribution like this, which represents how long the material has been in the part. You can see that the blue material represents the longest time, and the red material at the melt entrance indicates the shortest time. Instead of just looking at the color distribution, I prefer to look at the animation of the plastic progression through the geometry. To do that, we're going to go to the Result tab. There's two ways that you can do that. Actually, if you follow the procedure that we've been following up until this point, to the right of the Run button actually is the Result button, which will just bring you straight to the Result tab. You could actually just click on the Result tab manually. There's nothing wrong with that. But just so you know that the structure of the ribbon is such that we follow from left to right all the way through. Now, when we get into the Result tab, it's more of just picking and choosing which results we want to use or which result tools we want to use. And actually, as far as the animation is concerned, we have a toolbar all the way at the left side of the Result tab. And then I can press the play button, and that will play the animation of the melt front progression through my geometry. You can pause this animation. You can use the slider to figure out where in the geometry you want to be. Actually, new in I believe this was the 2024 version, you can use, instead of time percent, you can use volume percent. And you can also specify a range that you want to use for your animation. So for example, if I want to hone into a very specific feature at the end of fill, maybe I could use 95% as my lowest point, and then I can just show the animation of those last 5%. And it gives me a lot higher resolution of that filling progression. You can export this animation. If you go to the video dropdown, you can go to video and melt front, and that will allow you to create an animation of the melt front progression. You can import that into a report or whatever you'd like. Now, something that's very important to note about the flow front progression is fill balance. That's usually the biggest thing that we want to get out of the flow progression. I'm not just trying to see the pretty colors. I'm not just trying to see what's happening with the movement of the plastic. I'm really trying to interpret what's happening with the flow progression and how that's impacting the quality of my part. Ultimately, I want to make the flow as balanced as possible across my geometry. And when I say flow balance, what I mean is I'm trying to get all of my end of fills to fill out at the same time. If I pull back my animation just a little bit, we can actually see that this side of my part is filling almost at the exact same time as this side of my part. if I shift my gate location a little bit, even if I change my melt temperature, there's a lot of things that you can do. Usually gate location is the primary one, but there's a lot of things that you can do to impact this flow balance. And it usually takes a few iterations to figure out where the ideal gate location is, or what is your ideal processing condition to achieve this flow balance. Now, usually when I'm looking at flow balance, I don't try to go to the 99.5% of my fill. Actually, instead, usually I'll go to, I'll make the minimum back to 0. And I usually go to the 95% mark. The 95% mark is a good generic point of reference so that we can figure out if our part is balanced or not, or if the flow across our part is balanced or not. If both end of fills are unfilled at this point, that means that I have a pretty good flow balance. And the further I can push this, the better my flow balance is. The further I can push this while having both end of fills unfilled, the better my flow balance is. Now, theoretically, I could just put my gate location all the way on one side of my part. I don't really have to worry about flow balance because there's only one place for the plastic to go. However, the pressure loss through my cavity is also a concern that we need to consider as well. So I'm actually going to overlay my sprue pressure plot with my melt front progression so that I can figure out what's happening, how much pressure is required to make this part, and ultimately, is there any notable sections of my flow progression that are causing a drastic increase in my pressure. All right, so to get to the pressure plot, I'm going to go to filling all the way down to the bottom of the filling section. I'm going to go to XY curve. All right, and then in XY curve, I'm going to go to sprue pressure. That's actually the first one that'll show up here. The nice thing is that will overlay with your flow front progression. And so actually, if I pull back my melt front progression, you can see that there's a dashed line that moves across your sprue pressure plot. And so you can figure out exactly where you're at. All right, so the sprue pressure plot is split into 3 sections pretty much. We have the feed section, which is your runner. We have the parts, which is the majority of this curve. And then we have the VP switch, or the transition from our velocity control stage, which is our filling stage, to the pressure control stage, which is our packing stage. This VP switch is something that's specified over in the process. If you remember, we set, when we were looking at the process, it was set to 98% volume filled. And so that's what we're looking at here. Keep in mind that this is a time, not a volume. So maybe this isn't 98% of the total time-wise scale here, but it is 98% fill percent. 98% fill. All right, so what I'm going to do is I'm going to look for certain anomalies along the way of our flow. And so if I move this gradually, I'm using the slider up here at the top left under our animation toolbar. If I move over to just before this little spike happens, interestingly enough, we can actually see that there's an end of fill that's occurring kind of in the middle of our part. The middle of our flow progression, I should say. It's kind of on the corner of the part. And this is actually a good representation of what could happen in a more extreme condition where one of my end of fills fills out significantly quicker than the other. What happens at one of these end of fills is all of the momentum that was going in that direction has to quickly shift to going towards either in this part's case, either going towards the left side or the bottom right side. And if that momentum shift occurs through the gates, then we end up getting this instantaneous or impulsive spike in our pressure. Now, if it happens in the middle of the filling pattern like this, that spike isn't too important. However, if this spike were to happen closer to the end of fill, you can imagine that the spike actually goes up above the intended maximum pressure. One, that can increase the pressure requirement for this part, but two, that can really start to hurt your machine in the long term. And so we try to avoid any sort of pressure spikes right before the switchover. And that's the primary reason why we look at flow balance, to make sure that we can eliminate any of these pressure spikes. All right, you can actually you can close out of the pressure plot by just going up to the top right corner of the pressure plot and hitting the red X. There's one other result item that I want to show off in the filling stage, and that is the temperature results. One of the other goals when we're looking at the filling analysis is to figure out how much shear occurred as the plastic flowed through our geometry. Because the plastic has such a high viscosity and is a non-Newtonian fluid, the plastic will incur a temperature variation through the thickness, and we want to be able to not only visualize that temperature variation, but if there's enough shear, it can actually happen where the temperature increases as the plastic flows, and that can cause a drastically different shrinkage rate between the different sections of your part, which will play into the final warpage of your part geometry. So this is a very important characteristic to review when we're thinking about the final warpage of our parts. Now, what I'm seeing here is actually just the surface result of temperature. This is the temperature of the material that is in contact with the mold steel. Remember that in Moldex3D, we use a 3D type of solver. That means that we don't only have the results on the surface, we also have the results through the thickness of our part geometry. And so we have a few tools that help us to visualize that information through the thickness. Oh, I'm going to change my units over here to Celsius just to make it a little bit more readable. And then the tools that we're going to use, the first one is actually called the clipping tool. Over in the inspection area of the result tab, I'm going to use the clipping tool, which effectively just takes a cross section of my geometry based on a plane. I can move this plane up and down by just left click dragging. I can also change the orientation of this plane by going up to the top left corner and using these toggles up here. For example, if I wanted the XZ, which is perpendicular to flow direction, over in this area of the part at least, then I could do that. And if I zoom in on that cross section, we'll be able to see that temperature variation through the thickness where the core of our part is significantly hotter than the surface of our part, or what we refer to as the skin. This temperature variation will always happen with plastics molding. You'll always get a hotter core than the surface, at least from the filling results. But our job as analysts isn't just to look at the colors, it's to interpret what the colors actually mean as it applies to the final molded part. Now, this cross section is great, being that we're able to see the information through the thickness, but it doesn't actually give me too much information as far as how the temperature changed from one area of the part to the other. Actually, there's a better way to visualize this. I'm going to exit out of the clipping tool, and I'm going to go to the tool right below the clipping tool called slicing. And actually, fundamentally, the slicing tool does a very similar thing. It just takes a cross section of our part, except instead of removing one half of our part, it projects the result onto a plane. I can move this plane similarly to the clipping tool by just left click dragging it. And I can also change the orientation, which I will absolutely do in this case, to the XZ. But contrasting to the clipping tool, the benefit of the slicing tool is the ability to place multiple slices along a designated direction. So for example, let's say I wanted 10 planes instead of just one. Let's say I wanted 10 slicing planes in this direction. I can also do that transverse to that. I can go to the XY. I can place 10 planes in the XY. And that gives me a nice grid so I can see what's happening temperature-wise across my entire geometry, but through the thickness instead of just looking at the surface plot. The planes themselves kind of get in the way, so I'm going to uncheck the show plane checkbox. All right, now we can see a little bit more information across my geometry. However, it looks like the core is pretty much just like that dark orange to red color. So I'm going to adjust my scale a little bit so I can see the diversity of color a little bit better through my geometry. Once again, to adjust the scale, kind of like what we did with thickness earlier, I'm going to left click drag on the extent of the scale. In this case, I'm going to move the minimum upwards, seeing as most of the result that I'm interested in is towards the maximum side of the scale. I'm going to move my minimum towards that. That allows me to see this color variation a little bit more obviously. And actually, in this case, we can see that the temperature at the end of fill is hotter or is higher than the gate location, which is kind of counterintuitive. You would think that the heating source is at the melt entrance and the material or that heat, that energy should be releasing out into the mold as the material flows, which means that the material's temperature should decrease over the length of fill. But actually, the shear heating effect in this case caused the temperature to increase over the length of fill, which is likely a proponent of the filling speed that we elected to use in our process. This here is what we call the shear effect. The energy released into the mold is what we call the cooling effect. And so which of these effects is dominant will dictate which area of our part is the hottest. You can see that in this case, the end of fill is the hottest, so therefore the shear effect dominated. If the temperature decreased over the length of fill, which admittedly is the more common scenario, then we could say that this was a cooling dominated flow. And the most important thing to remember when we're looking at a temperature plot, and this is actually going to apply to pressure as well, temperature and pressure both play into the shrinkage variation of our parts. Any variation in shrinkage across our geometry will result in warpage. That's the ultimate goal here, is to figure out what the final quality of our part is. I don't necessarily care just about the temperature distribution. I care about this temperature distribution as it applies to the shrinkage of our part, and that shrinkage of our part as it applies to the final warpage that we're going to see across our geometry. All right, so the area out here, the hotter material is going to be at a higher shrinkage rate. So this area is going to shrink more than the gate location. This area at the end of fill over here is going to shrink more than the gate location. And so that can result in warpage by itself. This is an effect that's very important to take a look at. And this, what I call the slicing grid, is the best methodology to be able to visualize this temperature variation through our geometry. All right, so that's all I'm going to go through with filling. There's obviously a lot more results in filling that you can look at. And I have a great video up on our YouTube channel that goes through all of the results that I'm going through in this training. I go through those in even more detail in those videos. So I highly recommend you to take a look at those. But for the time being, we're going to go into the packing results. I'm going to get out of the slicing grid. I'm going to go into the packing results. Now the packing stage represents a constant pressure being applied from the screw. And so I want to see how that pressure is distributed through our geometry. So I'm going to go into the packing results, and then I'm going to go to pressure. In an ideal world, this pressure is distributed evenly across my geometry. If the pressure is distributed evenly, then that means that my shrinkage rate is going to be as even as possible. If I see that the pressure is concentrated around the gate, well, that means that the area around my gate is going to be at a pretty low shrinkage. But then the area out at the end of fill is going to be at a relatively high shrinkage. Once again, just like I talked about with temperature, that shrinkage variation will result in some amount of warpage. But okay, so I see that the temperature is a little bit localized around the gate. So why is that the case, right? Because we're applying the pressure from the melt entrance or from the screw. That pressure should be evenly distributed through the geometry. But the biggest thing to note about packing is that the pressure that we're applying from the melt entrance can only be distributed through molten material. Once the structure of our polymeric profile solidifies, it's no longer able to distribute the pressure that we're applying from the melt entrance. And so what our job is here is to figure out when the packing distribution is no longer, or when the molten material in our part is no longer able to distribute the packing pressure effectively. We can do this by looking at a result that specifically looks at where the molten material is in our geometry, and that's called the molten core. But before I go to molten core, I'm actually going to show off a really cool feature in Moldex3D that allows us to put two results side by side, and that's called the compare tool. Fundamentally, The compare tool, which is all the way over on the right side of the result tab. The compare tool allows us to compare two different simulation results to one another, but we can also use it to just put two results in the same simulation run side by side. And that helps us to get a meaningful comparison or meaningful translation of the data from one result to the other. All right, so I'm going to go into the compare tool. That's going to split our window into two. I'm going to keep one side as the packing pressure result, and I'm going to move the other side to be the molten core result. You can make this window as the active window by just left clicking there. You can switch which one is the active window by just left clicking, and you'll see that some items are available. All right, so once and so in the right window here, I'm going to put the molten core result item. The molten core shows us where the molten material is in our geometry. So all of this blue material represents molten material. All of the transparent areas are frozen. And so when I'm applying my packing pressure at this point in my cycle, which is 12 seconds into my cycle, 2 seconds of filling and 10 seconds of packing in this case, I end up getting a distribution of molten material that looks something like this. If you remember from the thickness distribution, this is the thick area of the part, so it makes sense that it takes a little bit longer to freeze. But the rest of the part at this point is already frozen. And so the only area that we're distributing the pressure from the melt entrance to is around the gate location. It's not able to distribute out to the rest of the part. You can actually see that some of the material over here is still molten, but there's no way for the material or the pressure that we're applying from the melt entrance, there's no way for that to get over to that molten area because the intermediate area here is already frozen off. And so at this point, if I continue to pack at the same pressure, I will probably get an overpacking around the gate, and that will cause not only visual defects from around the gate, but it can also cause a lot of warpage problems with the part coming out of the mold. Now, I've mentioned up until this point that the temperature distribution impacts the shrinkage rate, the pressure distribution impacts the shrinkage rate, but we actually do have a result that allows us to visualize that shrinkage rate directly, and that is the volumetric shrinkage result. I'm going to get out of the compare tool for this. You can just hit the compare again to toggle off the split window display there. And so if I go into the volumetric shrinkage result, we can get an idea of what areas are shrinking more than others. Keep in mind that the material that we're seeing here, kind of like what we saw with the temperature result, the material that we're, or the information that we're seeing here is just on the surface of the part, not through the thickness. And so kind of like the temperature result, I also prefer to use a slicing grid for the shrinkage to figure out what areas of the part are shrinking more than others. And we can see that generally speaking, the area around our gate is pretty low shrinkage. The area at the end of fill is high shrinkage. We need to think about why that is, right? The temperature of our material in the filling stage was highest at the end of fill, which the higher temperature material is going to be at a higher shrinkage rate. So it makes sense that the material over here is at a high shrinkage. But compounding with that, we also have the packing effect where we had a lot of packing around our gate location, our gating region. But the material over here, maybe the material intermediate around this area froze off, and that isolated the hot material at the end of fill from our gates. And that causes the material also to be at a higher shrinkage rate at the end of fill than the gate location. And so we get kind of this double whammy that happens. And this is why we don't really like the shear dominated flow like we saw in the filling stage. We get this double whammy where the shrinkage rate at the end of fill is significantly higher than the shrinkage rate around the gate location. And that shrinkage variation that we're seeing here will likely result in warpage. All right, so that's all I'm going to go into in the packing stage. That's the primary results that we take a look at in the packing stage, but there are obviously a lot of other results. If you're ever interested in a particular result item, what it does, you can simply just double click on that item. You'll get a nice description of what that item does. And for some of the more, I'll say, important results. Not that none of the results, all the results are important to some degree, but some of the more commonly used results, I'll say, will have what you can get out of that result. You'll get a really good description up in here. And then also you can see a statistics plot. I got to this by just double clicking on that result item, and you can see that description and all that stuff. All right, so moving down into the cooling stage. Now, in the cooling stage, we're pretty much just interested in heat transfer. And particularly, we're interested in heat transfer from the mold steel into the surface of the part. And I say it that way because it's very important to note that in the cooling stage, we pretty rarely care about what's happening through the thickness. We really care about how the heat transfer from our cooling channel system is impacting the temperature distribution across the surface of our parts. I'd like to show a nice pictorial representation of how the temperature distribution across our part impacts warpage. All right, you might have seen this example in a couple of textbooks, but maybe not quite in the detail that I'm going to show how this relationship relays information over into the warpage solver. But before I go too far, let's say I have a plaque. The top side is hot and the bottom side is cold. Maybe these are like 10 degrees different from one another. They're not significantly different from one another, but different enough. Let's say 10 degrees Celsius from one another. Which way do you think the part is going to warp? Is it going to warp upwards or is it going to warp downwards? You can write an answer in the chat if you'd like, or if you just have an answer in your head, that is fine too. To answer this question of which way the part's going to warp, we can look at the PVT plot. Now, the PVT plot is honestly quite complex by nature, but we can break this PVT plot down actually quite easily. PVT stands for pressure, volume, temperature. Those are the three variables that we're looking at here. We have volume over on the y-axis, we have temperature on the x-axis, and we have pressure, which is kind of like the third axis. These are the different curves that you see here are representative of different pressures. In this case, we're talking about temperature, so we'll just isolate out pressure and we'll just use the zero pressure curve just as an example. All right, if I have two different temperatures on the cavity and core side of my parts, that's going to correlate to two different points on this zero pressure curve. And if I draw the arrow over to our volume, that's going to correlate to two different starting volumes for the material in those locations respectively. Ultimately, the part that we're molding will equilibrate down to the room temperature. I'm going to call it the eject temperature just because that's the terminology that we use in Moldex3D. However, you can think about this as room temperature or uh, there's a few other terms that I've seen tossed around, but room temperature is the most common one. You can think about this as room temperature, this guy right here, and that's going to correlate to some sort of final volume. The distance along the y-axis that we have to travel to get down to this final temperature, this final room temperature, is going to be dependent on where we started from. We're all of the elements in my, or all of the areas of my part are getting down to this equilibrative temperature. And so the distance that we travel along this y-axis is dependent on pretty much our starting point. So we can see that the distance we have to travel is higher for the hot material, lower for the cold material, and that's representative of our shrinkage rate. You've probably heard of shrinkage rate a lot with plastics. This is where that's pretty much derived from, is how much of a difference there is between the hot state of the material and the cold state of the material. Now, the shrinkage rate of the hotter material is higher than the shrinkage rate of the colder material, as we can tell from how far we have to travel along the y-axis. And so pictorially, what that means is that the higher, or the material on the top side is going to pull inwards more than the material on the bottom side, and that's going to cause the part to warp upwards. This is what we call the differential temperature effect, and this is primarily why we need to include some sort of cooling system into our analysis, because otherwise we would assume that the part surface temperature is completely uniform, and that isolates out this differential temperature effect completely from the analysis. And that's a huge component to warpage. We'll end up getting a lot lower of a warpage number in the simulation than you might see in reality, and it could be misleading. You could go down a rabbit hole of trying to figure out why warpage is happening that wouldn't happen in reality, strictly because you didn't include a cooling system. All right, so to figure out what our surface temperature distribution looks like, we can quite literally just look at the first result in the cooling stage, which is called temperature. And once again, I'm going to change this to Celsius. Like I said, in the 2025 version, you can change the units on the fly pretty easily, which is really nice. But we can see that the surface temperature of our part is pretty much all at the blue side of our scale, the bottom side of our scale. And so to make the color distribution pop a little bit more, I'm going to bring the top of my scale downwards. You can just left click drag once again, the top of your scale downwards to be able to see that color distribution a little bit more meaningfully. All right, so we can see some areas of on the surface of my part are quite a bit warmer than the rest. Like down here in this pocket, we see that the temperature distribution is quite a bit warmer than the rest of the part. That's an indication that heat is trapped in that area and is not able to be extracted by the cooling system. To visualize this a little bit better, let's actually show the cooling system. To do so, we're going to go over to the model tree. We haven't really interacted with the model tree too much to this point, but the model tree is where all of the components and all of the attributions lie from the analysis. So if I want to show, for example, my cooling system, my mold base, all of that information you can access directly from the model tree. If I want to turn on my cooling channels, I can just turn on the radio button here, and it'll show all of the cooling channels that I have available for this system. Unlike the model setup that we did for the project earlier on, we use kind of straight channels across our mold. In this case, I actually got a little bit more conformal with the cooling channels. The cooling channels go quite a bit closer to the surface of the part. What we can actually see, if I recreate that temperature distribution that we saw earlier, we can see that that heat accumulation happens between the inlet and outlet of this cooling channel going on the bottom side, which is interesting. You would almost think that the heat would be attracted to this cooling channel, but it is not. It is actually going to prefer, to personify it a little bit, it's going to prefer to stay in the mold, and it will accumulate over a large number of cycles. This is going to create a hot spot in the mold, therefore a hot spot on the surface of the part, and therefore a differential temperature of the part that will apply similar to our example from our plaque. All right, so this is a huge deal. This is something that is going to very likely cause some sort of warpage. And also on the top side here, we see that there's a hot spot happening in this corner. And that's probably just because there isn't a cooling channel that gets close enough to there. Maybe I could add like a baffle, or I could bend this cooling channel down a little bit closer to the surface of the part. It really depends on the actions of the mold and what type of space we have, but we might be able to get the cooling channel a little bit more, a little bit closer to the part surface, and therefore get the heat transfer rate a little bit higher in that area. Now, as far as the PVT effect is concerned, we were looking more at the difference in temperature between the top side of our part and the bottom side of our part. And actually, we do have a result item that displays this directly. That is called the mold temperature difference result. Mold temperature difference quite literally just takes the temperature value on the top side, the temperature value on the bottom side, and takes the difference between those two. Now, we usually like to stay within 10 degrees between the top side or the cavity side and the bottom side or the core side. We want to stay within 10 degrees of difference between those two. That's 10 degrees Celsius, which I guess it doesn't matter as far as Kelvin or Celsius. They should be the same. We can see some areas of the parts. We can see some like over here. Maybe there's a really high temperature on the inside here just because there's no cooling. Obviously, it's too small for a cooling component to get in there. Maybe if I had like a beryllium copper core, I could put up in there, but might not be worth it. So I'm going to ignore these areas. I'm looking more at the general surface of my parts, not looking into the specific features. And so I'm actually going to move my scale, the top of my scale downwards. You can see kind of a trend with the cooling results. You do end up moving the scale quite a bit. All right, so we can see this area here is something like 19 degrees difference between the upper or the side of the part closest to us here and the bottom side of the part. We already know from the temperature result that this area is a lot hotter than the top side of the part. So it's not too surprising to me that there's a high temperature difference there. All right, and it looks like there's some other areas that might be outside of that tolerance. Actually, another thing that you can do here is you can specify the maximum that you want on the scale. So for example, I have a tolerance of 10 degrees Celsius. I can just make 10 degrees Celsius as the maximum on my scale. And then visually, any area that is outside of the scale, anything that is greater than 10 degrees Celsius, will show as transparent. And so this is a really good graphical representation of which areas of the part need some help. All right, so it makes sense that these two areas here have a high mold temperature difference. We saw that those were pretty obviously the hotspot regions. But we actually see a pretty significant mold temperature difference over in this area, which kind of like earlier, I'm going to use the compare tool. I'm going to keep this mold temperature difference the way it is, but I can go into the temperature result to inspect what is actually happening over here to cause that mold temperature difference to be a little bit higher. I guess I'll keep the cooling channels for now just to get an idea of what that effect looks like. All right, and I'll move my scale downwards. Yeah, so we can see even over here is a lot hotter than over here, but we don't really see that high mold temperature difference in this area. Maybe that's because there's a higher temperature on the top side. But over here, we actually see that there's a much lower temperature in this area with respect to the rest of the part. This is something that gets overshadowed a lot and overlooked a lot when simulation is being reviewed. This is what I would refer to as a cold spot. This is where there's actually too much heat being extracted by the cooling channels with respect to what's happening across the rest of the part. And so the temperature is much lower on the top side than I'll say the more nominal temperature on the bottom side. As far as the PVT relationship is concerned, it doesn't care if this is a hot spot versus a nominal spot or a cold spot with respect to a nominal spot. It just cares about the delta between the temperatures on the top side and the bottom side. And so even though this area over here has a concern from accumulation of heat, this area over here has a concern because of too much heat removal, which sounds pretty funny, but it is actually a very serious thing that happens with a lot of parts. And it's something that the mold temperature difference is really helpful in being able to recognize. All right, so as far as cooling goes, there is one more thing that I want to show off, and that is the ability to see the temperature distribution through the mold. So I'm going to go over to the model tab and turn on the mold base. So we turned on the cooling channels earlier. I'm going to turn on the mold base, which you remember is that box that goes around our part. Remember that we use 3D mesh for everything. We don't only use the 3D mesh for the melt system, we also use 3D mesh for the cooling system, which gives us the capability to see the temperature distribution across our thermal system. In addition to the parts, we can also see it across the mold and the cooling channels. Now here, I'm just looking at the surface of the mold, and the mold is transparent by default. So first of all, I'm going to turn off the transparency of the mold using this button here. There's a little toolbar up at the top middle of the modeling window. You can use the rightmost button in that toolbar to get rid of the transparency. And then I'm going to use the clipping tool. We actually used this earlier. I'm going to use the clipping tool to section off our mold. So you can kind of see some faint lighter blue areas, but kind of like earlier, I am going to reduce the scale so I can see that distribution in my mold a little bit easier. So as I move this across, you can see that hot spot in the mold right here, not only on the surface of the part, but you can also see it in the mold itself. And move my my maximum a little bit too low. You can see that maximum temperature, that hot spot in the mold happening between the inlet here and the outlet here. This is a really good way for you to visualize those areas that are hot and how the proximity of the cooling channel is impacting where that heat accumulation effect occurs. Kind of like the melt front animation, you can also output the animation of this temperature distribution over time. So if I wanted to get a feel for what that heat accumulation looks like over the cycle, you can go to results, and then under the animation video dropdown, you can use a time series animation. And what it's going to do is it's going to save an animation of this cross section at each of what we call the time steps through your analysis. And so you can see that my analysis here, the cycle time is 22 seconds. If I go back to my temperature result and I right click on that particular result, you can see all the time steps that we have available to us. And so what it's going to do is it's going to go through each one of these time steps and output a screenshot of this cross-section with this temperature distribution, and it's going to play that as an animation. So it's a really cool way to represent the cycle-wise information across the mold and figure out what is actually causing this heat accumulation effect. That's a really effective way to do that. All right, so we've looked at the filling results. We've looked at the packing results. That gave us a good idea as far as what the shrinkage was from the filling process and from the packing distribution as our material began to freeze. We looked at the cooling effect to look at the differential temperature across the bottom part, the bottom side of our part, and the top side of our part. And now we can go in and figure out what's going on as far as warpage. This is the section of result interpretation that I think gets mixed up a lot. I think a lot of people will go run their warpage analysis, and the first thing that they look at when the warpage analysis is completed is what the warpage looks like. And that is the wrong way to go about it. You really do want to interpret the filling, packing, and cooling first, then go into warpage to see what the effect is, or to see if what you expect is going to happen from the filling, packing, and cooling. If that actually does happen in the warpage results, then that's great. If it doesn't, at least you have a methodology for figuring out what is the true cause of that warpage. If I just look at the warpage results immediately, I'm going to see a color distribution. I'm going to try to find where the highest warpage is. And I'm going to start looking for what is causing that high warpage. But that will enable me to ignore a lot of extremely important effects of things that are happening across my parts. So it's extremely important that you go through the filling, packing, and cooling results before looking at the warpage results to get a premonition of what's happening or what the part's going to look like after the molding process. And that'll give you a much more structured and efficient result interpretation methodology rather than going on a wild goose chase by looking at the warpage results first. All right, so that being said, we're going to go into the warpage results. I'll turn off my cooling system, which would be my cooling channels and my mold base, just showing the parts. You could also get rid of the runner here. The runner doesn't have any information as far as the warpage is concerned. Change it to a more reasonable unit. All right, so the total displacement here represents how far each node moved from its original location. All right, so for example, this area over here had 1.26 millimeters of displacement. This area over here had maybe like 1 millimeter of displacement. And I say specifically displacement and not warpage because this is actually a combined effect where we have both the linear shrinkage of the material as well as the differential shrinkage of the material combined into one result. There is a natural shrinkage that the plastic is going to incur. That's something that we can't really do too much about. But what we can do something about is the differential shrinkage, which is like I was mentioning with the filling and the packing and the cooling. Those warpage effects are going to come from the molding properties that are applied throughout the process. All right, and so our job here is to figure out what the part actually looks like and which displacement are we actually looking at? Are we looking at the displacement because of linear shrinkage or because of warpage? That's something that we can interpret through these results. All right, so in the total displacement, I'm going to use a very nice tool that's called the deformation function. It's over in the warp section of the result tab. I'm going to go to warp and deformation. Fundamentally, what this allows us to do is deform the mesh, showing us what the final part looks like with respect to the original part. So the transparent geometry is the original part, and the new colored geometry is the deformed mesh. And that's a prediction of what Moldex3D is giving as the output part from the mold. Now, in most cases, the warpage is actually quite small with respect to the part geometry. And so as analysts, we want to exaggerate this warpage and figure out what the trend looks like across the geometry. And so most of the time, I will change what's called the scale factor. The scale factor allows us to amplify the amount of displacement that shows here so that we can visualize that trend a little bit easier. I usually use a 10 times scale. That's usually enough. Anything more than that gets kind of ridiculous. But anything smaller than that usually doesn't show the amount of trend-wise warpage that we would want to see. Now on this part, we have two high displacement regions, and those correlate to the two end of fill regions. That's pretty typical. So let's interpret both of those. If I rotate to the side, I can see that, okay, yep, there's a lot of displacement in the linear direction, or in the flow direction. There isn't a whole lot of displacement out of plane going in the X direction. There also doesn't seem to be a lot of displacement in the Z direction, the cross flow direction. So to me, this pretty much just looks like linear shrinkage. It just looks like this area is shrinking inwards towards the center of the part, which is pretty natural. There is a natural material shrinkage that will occur. But this definitely seems like a lot higher of an amount of displacement than the rest of the part. That could just be because of an accumulation effect of the length of flow. This is the highest length of flow, so maybe it has the highest displacement just because of that. But it does seem like it's a little bit higher than the rest of the part. And that might be because of what we saw in the filling and packing stage, where we expect that the shrinkage rate is quite a bit higher out towards the end of fill. Down here at the other side of the part, we can actually very obviously see that this part is warping. And so this wall is collapsing inwards. And that's likely because there was a hot spot down here. Like we saw with the plaque earlier, the part will warp towards the hotter region. And unfortunately for this wall, it's the only one with the degree of freedom to displace in the way that it does. And so we see that wall kind of collapsing inwards. Again, this is 10 times scaled, but this is a good indication of, if I have a tolerance that I need to hit, for example, if this window needs to fit into something, then I can get an idea of what areas of my part are going to be contributing to this, to the part being out of spec. But interestingly enough, this area over here has a displacement value of, let's say, like 1.1, maybe a little bit higher than that. This area over here has a displacement, the maximum displacement of 1.2 millimeters. But it looks like they are completely different effects. It looks like a linear shrinkage here, and it looks like clearly a differential shrinkage or a warpage over here. So how do we separate between the two? That's actually where the mold compensation comes into play. Mold compensation allows us to compensate for the natural material shrinkage, effectively removing the linear shrinkage of the material, leaving behind just the differential shrinkage so that we can see what areas of the part are truly warping, isolating the areas of the part that are shrinking at a higher rate. I'll let you guys know that the shrinkage rate of this material is 5,000ths of an inch per inch, or 0.5%. So I'm going to input 0.5% into any of these. It's an isotropic compensation, so it'll apply uniformly in the X, Y, and Z direction. You can use an anisotropic if you wanted to apply them differently in the three directions. Once I apply this compensation, we actually see a very different picture. We see that this area of the part is still displacing quite a bit. This area of the part over here is displacing a little bit, but not nearly as much with respect to where it was in correlation to the opposite corner before. This is an indication to me, even a further indication, that this area of the part on the left side was displacing mostly because of the linear shrinkage, whereas this area of the part, this bottom right corner, is displacing almost purely because of warpage. All right. Now there are a couple of extra tools that we have to indicate whether we're within spec or not, and I'll go through those quickly in just a moment. But before we get out of the deformation tool, I do want to note the export deform model option. The export deform model, actually, this was very phenomenally improved in 2024, I'll say, because we have the option to export step files from this function. So you're able to export the deformed model as a step file from the simulation. But even more importantly than that, you can export the reverse deformed model from the simulation. What I would do is I would select the format as step file. This one was ran, this mesh was actually a little bit older, so it doesn't have the step file option, but any simulations ran in the most current version, which in 2024 or in 2025, once that releases next month, you will be able to export the step file, the reverse deformed step file, and that then you can bring that into your mold design and start designing around that specifically. So very, very nice improvement from the warpage solver. But I'm going to exit out of there, and I'm just going to show off a couple of extra functions that will help to determine whether this part is within spec or not. The first of those is kind of an inconspicuous function called the distance function. Over in the measurement section of the result tab, the distance function fundamentally just places two distance markers and measures the distance between those 2 points. However, if I'm in the warpage results, it actually not only gives me the distance between those 2 points, but the deformed distance between those 2 points, as well as the linear shrinkage between those 2 points. So very, very impactful function here. If I have a tolerance that I need to hit, I can use this function to figure out if I'm within spec or not. This distance marker shows up over in the model tree, and you can either turn it off or you can delete it if you wish. The other one that I want to show off here is flatness. Flatness allows us to visualize the deviation from a flatness plane. The way this function works, if I go into flatness, I can select an element on the surface of my part that will propagate automatically to the rest of that surface within a given tolerance. Save and close. The output from this is a flatness plane, and then the resulting deviation of this surface from that flatness plane. The flatness value that I get here is just a difference between the maximum and minimum on my scale. And so theoretically, if I have a perfectly flat surface, there's little to no deviation, and therefore the flatness value gets closer and closer to 0. All right, and then a couple of new features in 2025 that I'll show off are parallelism and perpendicularity. Parallelism allows me to create a datum plane. And then based on that datum plane and a select target number of group of elements, let's say I want to see if this surface here is parallel to this surface here. Then I can get a feel for how parallel these two surfaces are to one another. And just like the flatness, this parallelism value is the difference between the maximum and minimum. So if these surfaces are perfectly parallel to one another, then this value would get closer to 0. Perpendicularity works in a similar but opposite manner. Instead of looking at the parallelness of these two surfaces, it would look to see how close to 90 degrees they are from one another. All right, so that wraps up the content that I have for this standard training. I do thank everybody for taking a little bit of time out of their day and a significant time out of their week to be able to learn a little bit more about Moldex3D. If you'd like to continue your learning process, we have the Cruise training platform, which goes through a lot of the fundamentals of molding and how that molding, how those molding parameters can be visualized in the simulation to improve your part quality, to lower your cycle times, and ultimately save you money in the long run. You can scan this QR code up here if you want to get started using Cruise training, and he has a few demo videos that you can review just to get a little bit of a precursor for what information is available. There's over 120 lessons that are available up there. Cruise also has a bunch of also has a VR platform, and so you can actually go in the VR through like an Oculus. You can go through a molding a molding building and see the different areas interact with the mold. You can break open the mold and interact with the different components. You can visualize the molding process. It's a very very interesting way to look at the molding process from and the mechanics of molding from a fundamental standpoint. And then finally, I've referenced a couple of times our YouTube channel throughout this training. You can also go and follow us over on LinkedIn using either the QR code here for LinkedIn or the QR code over here for YouTube. We post a lot of tips and tricks over on our LinkedIn, and we also post what events and conferences we're going to be at over there. And then on YouTube, I put a lot of tutorials, version updates, what's new in the newest version. These things are all put up on the YouTube channel. Finally, if you do have any questions after this training, you can email us at cases.us@moldex3d.com. We'll be happy to help you however we can to get you started in your molding journey or to continue along and make your simulation setup and your simulation life as fluid and easy as possible. Once again, thank you everyone for joining the Moldex3D training, and hopefully we'll see you in the next event, conference, training, or if you just want to give us a call to say what's up, feel free to do that as well. Thanks everyone. All right, if you do have any questions, you can shoot those down into the chat section of Teams, and I'll be happy to answer those however you'd like. It's pretty much anything. Doesn't have to be with respect to the content that I went over, but if you do have any general questions, I can certainly help to answer those now. Thanks, Bruce. Hopefully we'll see you in the next session here. Thanks, Leonardo. Have a good one.
Thank you.
All right. If there's no additional questions, once again, you can always send an email to us. I'll be happy to answer your questions however I can at any point, not only in this training session and our future training sessions, but if there's no other questions for now, I'll end it off, and hopefully you guys have a great rest of your evening. We'll talk again soon. Bye.